Hello, everyone. So I was asked by a student of mine to help with some Csec Physics questions in the topic radioactivity. And I thought I would just go ahead and make a video to help those of you out there who might also have issues with the topic. So there are about 5 multiple choice questions. I'll be approaching each one of them in detail. Let's begin. The first one reads, a Geiger counter is placed 5 centimeters from a source and the activity corrected for background radiation is 60,000 becquerel. If it is moved to a distance of 50 centimeters from the source, the activity corrected for background radiation would be, and they have the options right there. Right. So to approach this particular question, we have to be familiar with a few key terms. And the first one, of course, has to be radioactivity. What is it? I think most of you are familiar with this. It's pretty simple. Radioactivity is the spontaneous disintegration. Another word for disintegration is decay or breakdown of unstable atomic nuclei. Do forgive my writing. I hope you are able to read it. All right, so when we talk about radioactivity, we're talking about the fact that these atoms are unstable. And they're unstable because they contain too much energy. In order to release that energy, the nucleus of that atom will break down. When it breaks down, you're going to have certain emissions. Those emissions can be in the form of one, an alpha particle, which has a mass of 4 and a charge of positive 2. An alpha particle is the same thing as a helium nucleus. You can also have a beta particle, which has a mass of 0 and a charge of negative 1. And a beta particle is the same thing as an electron. You can also have 3 here for us, gamma waves. And this is just a form of electromagnetic radiation, of course. We covered it when we did waves. All right. So how do we measure this radiation, the emissions? We do so using a sensing apparatus called a Geiger-Müller tube or a Geiger counter. This is essentially what it is. It's a tube that we place in front of or close to the source. When those emissions enter the tube, a current is generated. We have accessories connected to the Geiger-Müller tube, such as this rate meter right here. And what those accessories do is it interprets the current in a way that we can read. For example, the rate meter would be telling us the number of nuclear disintegrations per second. It could also be connected to a loudspeaker, as I said before, and that loudspeaker would just beep with more frequency the closer you get towards a radioactive source. All right, so we understand what the question meant by a Geiger counter and of course what is radiation. Something interesting is mentioned here, and that is the activity corrected for background radiation. Background radiation, what is that? Well, let me just put the term down here. It's simple. Whenever you are measuring the radiation coming from a source, what enters the tube is not just the radiation from the source, but also other sources from the Earth's atmosphere or from metals in the Earth. And all of this together is what will be read. So what's important to do is you need to know the radiation that is not coming from the source. All of that radiation that is not from the source is called background ionizing radiation. And once we know this, we can subtract this from the total that we get, and we know that what is left is the radiation just from the source right here. So they're saying that they've done all of that, they've corrected it, and this 60,000 becquerel is the radiation coming from just that source. I'll just mention for a moment that what a becquerel is comes from the 1860s thereabout, when scientists like Marie Curie and her husband Pierre and Henry Becquerel did instrumental work in framing what we know today to be radiation. And because of his work, Henry Becquerel got the SI unit BQ for, this simply means nuclear disintegrations per second. It's also written like this. So this is talking about the amount of times this nucleus breaks down every second. That's what it's referring to. Nothing difficult there. All right, so the question goes into saying that at first, the Geiger counter is placed 5 centimeters from the source. Say that this is the 5 centimeter here. And then after, oops, I think I disconnected my tablet. All right. And then after it is placed, that's it, 50 centimeters from the source. Of course, I am not drawing this to scale. This is just so I can illustrate what is going on. All right. Whenever you see these questions that alternate the distance between the Geiger counter, just write GM tube in these, the distance between the Geiger counter and the source that it is measuring, more often than not, it's referring to what we know as the inverse square law. Bear with me, I'll explain what all of this means. The inverse square law is represented by the formula 1 over r squared, or 1 over d squared, where the r stands for radius, or distance from the center, and d is for distance. It's the same thing. So what this is essentially saying is that the further you move the source from the Geiger-Müller tube, is the less intense the radioactive emissions that reach it. Let me just say that part again. So the further away you move the Geiger-Müller tube, is the less the readings, the less intense the radioactive emissions that actually reach the tube. And this makes a whole lot of sense. The further away you are from some radioactive source, the less radiation you're going to receive. And the formula right here just simply speaks to how much that radioactive intensity is going to decrease. How much it decreases is going to be the inverse squared of the distance. So let's look at what that means in terms of this question. Simply put, the distance would be the 5 centimeter, and we're comparing it to this change in distance right here. We realize that 50 centimeter is 10 times the distance of here. So it would really be 1 over 10, because it's 10 times our original distance, and it is squared, which would be the same thing as 1 over 100. What does this mean? It means that the source of the radiation, or the radioactive intensity, is going to be 100 times less if you move it 10 times the distance. And that's pretty neat. So this would be 1 over 100 times the original 60,000 becquerel, or nuclear activity. So if we look on the options that they've given us for the answers, A says 0 becquerel. This would mean that moving it 10 times the distance away, the amount of recorded activity would be 0. Of course, that's not true. Nope. All right. B says 60,000 becquerel. We started at 60,000 becquerel. So this would be saying that there would be no change in intensity. It would be the same. Of course, that can't be true. And the next one says less than 60,000 becquerel, but greater than 0. And this makes sense. It is going to be less than 60,000 as you move further away, but not quite 0 at the 50 centimeter mark. So we know that this fits. We just need to look at D to make sure that it's not the correct answer. And D says 30,000 becquerel. That's a half of this. Too specific and not correct. So the answer is C. Let's move on to the next question. All right, so let's look at the second question. And it reads, 6 kilograms of a radioisotope produces a count rate of 1,200 becquerel when the detector is placed 5 centimeters from a sample of a given mass. What would be the count rate produced at the same distance by a sample of 3 kilograms of the same radioisotope at the same time? All right, so let's start by illustrating what this question is asking. So that we have a 6 kilograms sample. Just draw a mass right here. And at this 6 kilogram sample, it's placed 5 centimeters from the detector, but that isn't changed. So we don't need to take it into account. But it has a count rate of 1,200 becquerel. And they're saying, what would be the count rate if for the same radioisotope, same substance, instead of 6 kilograms, we had 3 kilograms? What would the count rate be here? All right, this is fairly simple, and the answer to this, what we have to take into acknowledgement is that the count rate is directly proportional to the mass of the sample. So if we are decreasing the mass of the sample by half, what should happen to the count rate? You got it. It should also decrease by half. We should have 600 becquerel over here. The answer is right here for B. Let's look at number 3. A radioisotope has a half-life of 80 years. How long will it take for the activity to fall to 25% of the original value? All right, so I think to answer this question, we have to go to understand the concept of half-life. What do we mean by half-life? Do you know? Well, the half-life is the time taken for the mass or activity of the sample to decrease by 1/2 its original value. Fairly simple there. By saying that this radioisotope has a half-life of 80 years, we are saying it takes 80 years for half the mass or the activity in becquerels or nuclear disintegrations per second to decrease by half its number. That's fairly simple. So let's try to answer the question here. How long will it take for the activity to fall to 25%? Well, the activity starts at 100%, right? before any time has passed. And at 100%, it's going to move to a half its number, 50%, over a period of 80 years, because that's the half-life, right? So from 50%, what's a half of 50%? Yup, 25. How long does it take to move from the 50% to the 25? Again, it's a half of the activity, so it's another 80 years. If we add these two together, we get the total amount of years for it to move from 100% to 25%. 80 plus 80 is 160. There we go. The answer is B. All right, let's move to the other questions. All right, let's look at this question right here. Let me enlarge it a little bit. And it says, on Sunday, the corrected count rate of a radioactive source was 240 disintegrations per second. Exactly 2 days later, the rate has fallen to 120 disintegrations per second. What will the count rate be exactly 4 more days on Saturday, measured in becquerel? I already circled the answer for this, but I'm going to show you how we arrive there. Right. So let's start with where it is. It's at Sunday, and the count rate is 240 disintegrations per second. And after 2 days, that count rate has moved to 120 disintegrations per second. What does this mean? 120 is a half of 240. So the 2 days represents the half-life of the sample, because over 2 days, a half of the activity has been decreased. So let's go into what happens over the next 4 days. So after the next 2 days, it's going to decrease by half again. What's a half of 120? It is 60. And then over the next 2 days, it's going to decrease again. And what's a half of 60? It's going to be 30. So in the 4 days to come, it would decrease to 30. And that's why we have the answer being C there. All right, for number 16, if there are 128 neutrons in lead-210, how many neutrons are there in the nucleus of lead-206? All right, so what are lead-210 and lead-206? They are isotopes. And what's an isotope? They are atoms of the same elements the same atomic number, has a symbol Z, but different mass number, which has a symbol N. All right, so we understand what isotopes are, and we know that these are isotopes of each other. So what causes the change right here? What causes the change from 210 to 206, which is a difference of 4, is that we have the number of neutrons decreasing. They're not going to increase. They're going to be decreasing in order for the isotope to become stable. So originally, it started with having 128 neutrons. What's going to happen after it gets rid of 4? It's going to move from 128 to 124, and that's how we got the answer for that right there. All right, so I thought these questions were fairly simple, but they require knowledge of the content. I wish you all the best. If you have questions, if there are any problems with any topic, you can always reach out to me and I'll try my best to get back to you. All right, take care, all the best.